heavenly bodies like the sun or the moon to orient themselves in free flight. The idea is that they see the moon up in the sky and they try to keep themselves aligned at a certain angle with the moon. Now, because the moon is so far away, that angle pretty much stays the same as they fly along. Now, imagine we brought the moon down to the Earth. As he goes underneath, his viewing angle would change more rapidly, and he has to pitch up in order to compensate for it. This ends up pointing him just beyond the far edge of the light source. This would induce a logarithmic spiral.
Let's get going with the derivation part of the trajectory of the insect. Not as a function of time. Yeah, as a function of time. Wait. No, I'm talking about the trajectory, right? So I won't be talking in. No. Oh, sorry. Uh, Shit. Okay, shit. One, two, three, go. Let's get going with the derivation of the trajectory of the insect. So here I have assumed RT with the second. Here I have assumed RT as the distance of the insect from the light source as a function of time. It can be realized that the R varies linearly with time if we just consider the fact that the insect has to make a particular angle, say phi, which I have written here, phi, not 4, sorry, phi. Sorry, I'm not using stylus, so bear with me. So I've written is a function of phi and t, and here phi I have set to be constant and t is varying. Obviously time varies, right? Time is the flow of time is life, I think. Forget it, sorry. So the insect has to make a particular angle of its velocity vector with the direction vector from itself to the light source. That is phi that I've written here. So done for the uh, distance part. Remember, this is distance and not the displacement vector or the position vector, because position vector needs direction. Every vector needs direction, right? And I have only written the magnitude. So you can safely say that this is the magnitude of the position vector with respect to the light source. Now let's get going with the radial velocity part. We can safely assume that for a small interval dt, say dt, v cos dt would be negligible in comparison to r naught, and hence its variation can be neglected, hence with respect to r. So like this whole thing can be assumed to be constant for an interval of dt. Remember that dt is very small. So we can say that r into r as a function of time into dt, sorry, what the hell am I writing, sorry, d theta, which is a small displacement that has happened in the dt time, into r. Remember, this r I have assumed to be constant for a time interval of dt. Now as dt tends to 0, this approximation tends to be accurate. Obviously, I mean, tends to be perfect. So I can safely assume this thing as the distance traveled by the insect in the time dt, that is tangential to its position vector, and I can say this as v sine theta dt, sorry, it's out of the page, sorry. Now bring dt over here, and what you have found is this one, this little equation that you see right here. So this equation is done. Now plugging in the value of r as a function of time into this equation and solving it yields theta as a function of time as this. function. So after getting the value of theta as a function of time, we can substitute time as a function of theta. Trying to do so, we can divide the whole of this equation by tan theta. So tan theta comes here and we end up in this equation, right? After that, what we can do is we can take e to the power this much is equal to e to the power that much, which in turns yield this. Now we can separate t from this equation very easily, and we can substitute that in this equation. Doing so, the whole thing yields this little small equation. To visualize it, let's go to Desmos. The velocity of the fly makes with the position vector from itself to the light source as 0.9 radians. Let's see how it looks on the graph. Yeah, so initially it started from 5, went on a spiral to reach 0, and to be honest it will reach 0, it should reach 0 like quite fast, because the distance between itself and the light source decreases at a constant rate, so it will reach 0. And now let's tweak the parameters so that the initial angle that the velocity vector makes from with the position vector to be greater than 90 degree. So I think 1.5 will do it, right? Yeah, 1.5 will do it. No, maybe 1.6, 1.7, yeah. So as can be clearly seen from the graph, the particle actually recedes away, obviously, because the velocity of the particle along the direction vector is outwards and not inwards. So the spiral is opening out rather than closing in this case, as in this case. So yeah, I think that the equation is correct, and this is how it should move. And thanks for sticking till the end. Thanks. Bye. Peace out.